Today we are going to talk about atmospheric effects on optical observations, and specifically we are going to talk about atmospheric extinctions. Stars are actually brighter than what we observe them. Not all the light reaches us through the atmosphere. Some light is absorbed, some light is scattered. This is a plot of atmospheric transmission as a function of wavelengths going all the way from X-rays to radio, and you might have seen this plot before. Most of the X-rays are absorbed at the top of the atmosphere, so none of the light reaches the earth. So this is a plot of the transmission. 0% of the light reaches the ground. In visible, most of the light reaches to the ground, and you can have telescopes on the ground as well. And there are some windows in the infrared where the light reaches, but other windows where the light simply does not reach the ground at all. Again, in the radio, there is a huge window where light can reach the ground, and we have radio telescopes on earth. And at very, very low frequency radio, the ionosphere actually simply reflects radio waves off back into space. Now we are going to focus on the optical and infrared part of the regime and look at it in much more detail. There are different components of absorption and scattering. This is a plot of extinction as a function of wavelength. Extinction simply means the loss of light. What fraction of light is lost? Now this has units of magnitude by air mass, and we will talk about air mass in the next few slides. But let us talk about the components first. The major component of the atmospheric extinction, Rayleigh scattering. Rayleigh scattering is because of light interacting with molecules of air and simply scattering, and that is proportional to lambda to the minus 4. At long wavelengths, it is fairly unimportant. Towards lower wavelengths, towards blue, it becomes more and more important. So this curve here shows Rayleigh scattering. There are also aerosols, which are dust, water droplets and so on, which start becoming important towards the infrared. They become more important than Rayleigh scattering towards the infrared. And then there are these huge spectral features. You can see they are called telluric lines. These are absorption lines from water molecules, oxygen molecules and some other molecules, which show very, very large absorption features towards the infrared. There is also contribution from ozone towards the UV, but because it is not very significant in the optical, we can ignore that. Now all of this, you can notice, depends on air mass. The units here are magnitude per air mass. What this means is that for an air mass of 1 at, let us say, a wavelength of 4000 angstroms, you will get absorption of about 0.4 magnitudes. So we will talk about in more detail and work out through a problem of what that means. Simply put, air mass means how much air is the ray passing through relative to the zenith. So when a ray comes straight through, it is the minimum amount of air that it can pass through, and that we call as air mass 1. So air mass is the integral of the density of air across the path of the ray divided by the integral across the density of air if you are looking through zenith, right. For small zenith angles where zeta is about 25 to 30 degrees, you can approximate the atmosphere once again as a plane parallel slab of material, and if this vertical distance is considered to be unity, then it is fairly easy to see that at an angle zeta, the length of this ray will be sec zeta, and you can approximate air mass as sec of the zenith angle. Of course, as you go to higher zenith angles, the amount of air mass increases and the formulas are a little bit more complicated. But what does that mean? So how do you calculate effect of this extinction on the star's brightness? You remember that magnitudes are negative logarithmic, right. So every unit of extinction reduces the same fraction of light, corresponds to addition in magnitudes. So for example, for air mass 1 at a wavelength of 4000 angstroms or 400 nanometers, you have an extinction of 0.4. What that means is that a 3 magnitude star as observed above the atmosphere will appear 3.4 magnitude star on the ground. If you go further away from the zenith and your air mass, let us say, is 1.5, it will be 3.6 mag. So 0.4 mag from the first unit of air mass, and you have another half a unit of air mass that contributes another 0.2 magnitudes. So, the total magnitude which is observed will be 3.6 magnitudes. So, in summary, the atmosphere absorbs and scatters a fair bit of light, and this is extremely wavelength dependent. The delta magnitude which you get is proportional to the air mass, and if you go away from the zenith, the air mass increases, and so extinction will increase.